program?
Yes.
Okay, I'm pleased to introduce today's speaker. Dr. Bronson Messer was educated as a physicist at the University of Tennessee, where he earned his undergraduate and graduate degrees, finishing with a PhD in 2000. His earliest association with ORNL came at the tender age of 16 when he was a summer student at the lab. Bronson's primary research interests are in astrophysics, related to topics including the explosion mechanisms and phenomenology of supernovae, dense matter physics, and the details of turbulent nuclear combustion. He's worked on the application of machine learning algorithms to the analysis of galaxy merger simulations and on performance modeling and prediction for high-performance computing architectures. He holds a joint faculty appointment in the Physics and Astronomy department at UTK, but his primary day job is at ORNL, where he is a distinguished scientist and director of science at the Oak Ridge Leadership Computing Facility. In that latter capacity, Bronson is involved with a variety of scientific applications using ORNL supercomputers, namely the current Summit and the forthcoming Exascale Frontier. With no further ado, I will turn things over to Bronson Messer to tell us about computational science at the dawn of the exascale era. All yours.
Okay, just a minute. I'll get you to be the host here.
Okay. Ellen, thank you for that introduction. I'm going to take you on the road. I think that might be the nicest introduction anybody's ever crafted, and you crafted it because I don't think I gave you that text. So that was incredibly nice.
Here we go. So you are the host.
Okay, let's see. Oh, and it looks like I have the power now. Can everybody see my slides? The canonical Zoom question, and I see not.
Yes.
So I'll go ahead. So as Ellen said, I'm the director of science for the Oak Ridge Leadership Computing Facility. And I'm going to tell you a little bit about computational science in general, as we're standing here at the very precipice of what we're going to call the exascale era. And I'm going to explain all those terms to at least some degree of fidelity, I hope, in the early part of the talk to sort of set the stage. What I really want to drive home to you throughout this whole talk is one of the neato things that I think, one of the greatest things about supercomputing per se, is that they're very large, unique pieces of equipment, but they are absolutely Catholic in their purview. There's no field of science that the LCFs don't touch in some way. And I think that is a remarkable thing when it comes to unique scientific instrument, like a leadership computing facility. And I want to try to give you a flavor of that actually happening. So the outline, what I'm going to tell you, a little bit of an overview of what leadership computing, it is a term of art, but one that's sort of important to understand what it actually means. A little bit of history, of course, what we're building now, both hardware and software wise, which tends to be very important. Of course, I'm going to show you some recent scientific results, including some results that we've had around the pandemic. Something that's ruled all of our lives for the past couple of years, and a conclusion and a look forward. So what is the OLCF? It's a user facility at the laboratory. I think most people in this audience are very familiar with that concept. And our mission is to deploy and operate computational and data resources that are required to tackle global challenges. And we do so at a scale that's very much designed to be unprecedented, either in time or in space, if you will. At any given time, we're sort of designed to be the biggest supercomputer on the face of the planet. And part of what we do is, like I said before, investigate disciplines that range from engineering disciplines to astrophysics to earth systems to nanomaterials. And it's important that because the use of this facility it's unique, it's non-trivial to get the full efficient use out of it. And because of that, we very much view ourselves as partners with investigators who want to use the machine and trying to get that science done. The leadership computing facilities were born out of a specific federal law. The Department of Energy High-End Computing Revitalization Act of 2004 is what sort of gave us our birth. And the Secretary of Energy was directed to establish and operate the LCFs and then provide access to those to basically everyone, U.S. industry, institutions of higher education, national laboratories, other federal agencies. And we have even construed that to mean everybody else on the planet as well. We have several foreign projects on the machine in any given year as well, as long as they can sort of show that they have need and can use the resources. One thing it's a minor pedantic point, but there's actually one leadership computing facility that spans 2 sites, the Oak Ridge Leadership Computing Facility and the Argonne Leadership Computing Facility in the suburbs of Chicago. That was on purpose. One of the key advantages of such a strategy is that we're able to field computers sort of in a tick-tock sort of motion. We all know that computer technology advances pretty quickly. And so we tend to field computers, us and Argonne, in sort of this tick-tock fashion where they'll get ahead of us for 1/2 of a generation, then we'll catch up and surpass them. And at any given time, we want to have what's called a diversity of architectures. There's several different ways to achieve the same thing, to use the same technology to get answers. And we basically want to explore the space that is going to give us the most bang for the buck. Just so happens that in the very near future, that architectural diversity is actually going to converge a little bit on a very particular kind of technology that we actually at Oak Ridge sort of pioneered, and I'll tell you a little bit about that in a second. But again, just to reiterate, the 2 most important things about the LCFs is that projects receive ridiculous amounts of time. 10 to 100x more resources that are available at any NSF center, any other DOE center, any other supercomputing center on the face of the planet. And because of that, both LCF centers partner with users in this very fundamental and concrete way. We have an entire section of PhD domain scientists in various scientific fields who share nothing more than their love of being close to the machine, but partner directly with all the projects to make sure that the science actually gets done. They're sort of staff beamline scientists, if you're familiar from an accelerator point of view. But the supercomputer is their beamline in many ways. So our biggest resource right now is Summit. I'm going to guess that at least part of the audience has heard of Summit. It's gotten a lot of press because of its power. It was the #1 supercomputer for 18 months, I think, starting in 2018. It has a peak performance of 200 petaflops for double precision numbers. So if you don't know what a flop is, it's not a very hard concept once you sort of have it explained. A flop is a floating point operation per second. So take a number with a decimal point in it, another number with a decimal point in it, add or multiply them together and get the result out. I always like to say that our wetware, if you will, if you're really fast and facile, sort of operates at 1 flop. You can sort of do one of those operations in order a second, and that's an astrophysicist's second, right? Anything up to 10. Your brand new laptop, if you've gotten one in recent years, probably runs at 1 or 2 gigaflops, so 1 or 2 billion operations per second. So 200 petaflops is 200 times 1 times 10 to the 15 of those flops in a single second as a peak speed. It also has a peak of 3.3 exa operations using reduced precision math. That reduced precision math is useful for things like data analytics and artificial intelligence. And there's special pieces of hardware inside the machine that execute those instructions and make it that much faster. So how do you make a supercomputer? Well, you aggregate a bunch of smaller computers together. There's 4,608 nodes in Summit connected together with this very high-speed network so they can talk to each other. And then there's a 250 petabyte file system attached. Amazon, Facebook, Google, they have more disk space than that. What makes this particular file system a little different than what they have and very useful for science is if you're a scientist and you're logged into the machine and you look at that file system, it looks like one big disk drive. You don't have to worry yourself about having to place things on individual disks. It looks like there's one big 250 petabyte disk drive sitting out there waiting to receive your data or for you to be able to read from it. That's really, really, really useful. The nodes are kind of custom. They have 2 Power 9 processors, which is a particular kind of processor that IBM builds. And then arrayed around those CPUs are 6 NVIDIA Tesla V100 GPUs, graphical processing units. So if anybody, I don't think I saw anybody here on the call that I suspect is a PC gamer. But if you know a PC gamer, you know, in your family or among friends, they probably have the latest and greatest GPU stuck in their gaming rig, because GPUs are really, really good, it turns out, at modeling physics. And you need physics to have realistic games. The downside to GPUs, even though they're really fast and they're very energy efficient, is they're incredibly dumb. They're really stupid. I liken them to threshing machines, where they can do the same operation over and over and over again, but you ask them to make a decision and suddenly you've locked up the whole works. That's part of the reason that these so-called these beamline-like scientists in our liaison groups are so important, to be able to help people make use of that. The machine also has a lot of memory, over 600 gigabytes of fast memory attached to those GPUs. And then it also has these small, they're 1.6 terabyte drives hanging off each node to let you do local data storage. So that's sort of the speeds and feeds for the machine itself. To give you a hint about what that looks like, we're building a new machine. We're literally right in the middle of it, and I'm going to show you some pictures of that in just a second. For what we think will be the nation's first exascale computer. That is a machine that's capable of doing at least an exaflop at full precision in the very near future. It's a very similar machine in some ways to Summit. It has CPUs attached to GPUs, but in this case, it'll be AMD CPUs that are very much like what you probably bought in your latest laptop from Best Buy, and AMD GPUs as opposed to NVIDIA GPUs. And that introduces some interesting programming tricks that we have to do. Other than that, a lot of these speeds and feeds are very sort of similar, just scaled up from Summit. The storage, I think, is very impressive. It's going to be, say, 4 times the capacity of what we have on Summit. So approaching an exabyte of data, it will be storable off the machine. And we'll need it, because data always, like a gas, expands to fill the full volume that is available to it. This machine has required significant infrastructure around it. Infrastructure that's on a scale that you would expect for example, for a large accelerator facility. We've had to add 40 megawatts of power, so we actually had new power lines pulled over the ridge from a local substation, from a local TVA station. Literally tons of more cooling. Even though we're using warm water cooling to cool the machine, we still had to have chillers for backup and other things. A ton of electrical infrastructure. And what it's done is it's transformed this building that our computing center sits in right now. You know, especially if you were at the lab back when I started, you know, what used to be the parking lot, of course, we have new buildings in that quad, and it looks like a rather sedate office building from the outside, except now it sort of looks like a steampunk monstrosity, because it has pipes and wire conduits and stuff sort of sticking out of its shell all over the place, because we really had to put a lot more infrastructure in. But Frontier is being installed. Here's a look at one row, the back of one row of the machine. There'll be several of these rows in this data center very, very soon. Interestingly enough, if you compare the noise in this room, one of the interesting things to me anyway is that I can actually walk into this room and have a conversation with somebody, even with the machine running. And part of that's because of these sort of white things that you see interspersing in these cabinets, these coolant distribution units. The older machines used to basically have air conditioners setting on top of them to keep them cool. Whereas every part in this machine is liquid cooled. And basically these pumps run really, really quietly. It makes it a much more pleasant experience to be in the machine room for a long time. You're also not freezing to death because the air conditioner is cranked down to 50 degrees. So in general, there's been many years of work that have gone into fielding Summit first, all of its predecessor machines, and now into fielding Frontier. But one of the things that I really like to tell people is that maybe the hardware is the easy part. That's something that you can sort of go out, buy, aggregate, figure out how to do fairly straightforwardly, but actually having software that'll actually get you to scientific insight is perhaps the hard part. We do that in several different ways. One of the things that we've always done is we have what we call the Center for Accelerated Application Readiness. And I make no apologies for always deploying this pun, but CAR is our vehicle to demonstrate excellent performance for the next generation machine. So what we do for each one of these new machines that we get, we bring together teams around certain application codes, have them concentrate on porting and optimizing the code for the next architecture. We do it in a lot of different ways. We even as far as hiring postdocs just to work on these codes for a couple of years at a time to be able to make sure that they can take full advantage of the architectures. For this round, we have a stable of 8 codes that sort of span, not completely, not in a complete set, but do a pretty good job of spanning the kind of science that we see. Everything from astrophysics, specifically this Choyo code does galactic outflows, to molecular dynamics that you might use, for example, to look at the COVID-19 coronavirus, to material science, biology, fluid dynamics. This guess code, in fact, is what's called a DNS code, a direct numerical simulation code for turbulence, and we'll return to that theme in just a little while. Nuclear physics, coupled cluster methods that are also used in computational chemistry, for example, plasma physics, and subsurface flow. These teams have been working, again, for several years on these codes, and are now to the point where they're ready to actually, they're chomping at the bit to be able to get on the actual machine and start running them and try to get some new results out. Another important thing is every one of these code teams has a particular scientific question that they simply did not have the computational power on Summit to be able to figure out in a reasonable amount of time, that they're going to be able to figure out because we've fielded Frontier. So it's one thing to port the code, get it running fast. It's quite another to have a problem that's big enough that you want to attack. That's at least half the battle, to harken back to the PSAs from the 80s. Another part of software development for Frontier comes from DOE's Exascale program, the Exascale Computing Initiative, which has several components, including, fielding new exascale computers at each one of these computing centers. But this exascale computing project is mostly about software development, both the software that gets used by individual application codes and the application codes themselves. And so there's a large stable of order 20, almost 24, of these individual ECP codes that's, again, doing an even better job of spanning the space of scientific disciplines that make use of really high-end computing. Everything from stockpile stewardship to building turbine wind plants, material design for extreme environments for nuclear fission and fusion, subsurface, again, for carbon capture, biofuel catalyst design, additive manufacturing, of course, is a very popular topic nowadays and is highly computationally intensive. Seismic hazard and risk assessment is something that supercomputers do a really good job of, because they can actually keep track of, for example, every Fourier mode in the Earth as it shakes. Down to finding, predicting, and controlling materials and properties, of course, doing climate modeling, and attacking cancer from a computational point of view. Now, because you got me to give this talk, I'm going to concentrate on telling you about one of these projects because it's mine. And that's the one that's denoted here as demystifying the origin of the chemical elements. And the name of this project is Exastar. So this large team of people that sort of spans several national laboratories and universities, we all came together to try to build what we're calling a next generation code for stellar astrophysics, and especially explosive stellar astrophysics. That is, what happens when either a massive star dies in a core collapse supernova explosion, when two neutron stars coalesce and fuse and cause an outflow, a violent outflow after they've dissipated a lot of their energy due to gravitational waves. We're also investigating things like X-ray bursts, which is what happens basically when the neutron-rich ocean on top of accreting neutron star catches on nuclear fire, and type 1a supernovas, which is what happens when a star like our own sun, for example, dies as a white dwarf and then accretes material. We have several particular things we're going after. We want to be able to predict gravitational waves that you might be able to see with machines like LIGO and others. We also want to guide future nuclear physics experiments at facilities like FRIB, the facility for rare isotope beams that just went online at Michigan State University. It turns out that, trying to find out where all the gold in the universe came from requires, and all the uranium to be sure, requires us to have pretty precise measurements of things like neutron separation energies, beta decay rates, just general nuclear structure about really heavy elements. And these heavy elements, because they're relatively neutron rich, they have a lot of neutrons, they don't like to stick around very long. And having an experimental facility that allows us to get some of those cross-section measurements, for example, is a real boon. But there's a lot to choose from. So part of the job is to have simulations that are effective enough and precise enough, have high enough physical fidelity to be able to help the experimentalists guide what they're going to actually look at in the future. Also, things like core collapse supernovae and binary neutron star mergers are prodigious sources of neutrinos. Even more prodigious than we have if you look up in the sky right now, right? The sun is a fairly prodigious producer of neutrinos. If you hold your hand out, there's about 70 trillion neutrinos passing through your hand right now. They'll, of course, never interact with you or the Earth because they're the apotheosis of ghostly. They don't interact with matter very, very much. But it turns out that in the core of a star, where you're 2 to 3 times nuclear matter density, the mean free path for a neutrino is about 1 meter. And so they're the only things that carry energy from one spatial point to another in that situation. So that's what we're working on for Frontier. But what about things that are actually happening on Summit right now? Well, that same project, our first maiden voyage for at least pieces of this project has been to use our older core collapse supernova code to do the first few seconds of evolution of a core collapse supernova, but then use a version of our new code to actually carry that through until the shock wave that gets born deep in the heart of the star actually rips through the surface of the star and would produce what you would actually see as a supernova. So a prime example of a star that's going to go supernova is Betelgeuse, which I think everybody can find. It's the big red star in the shoulder of Orion. It could go supernova tonight. It could go supernova in 10 million years with equal probability, but it's within the next 10 million years, it's going to go supernova because that's the lifetime of a star of that size. When it does, it'll be brighter than the full moon for several weeks, and it'll be daylight visible for up to 6 months. So it'll be a fairly profound thing when we look at the sky. But we have to wait for the shock wave to actually get out. And we want to be able to trace exactly what elements are getting cooked up by the heating of that shock wave as it passes through stellar material. In the past, we've been able to afford to use literally a baker's dozen, 13 different nuclear species to be able to track that evolution. Because of GPUs and that large amount of memory that we have on machines like Summit and upcoming Frontier, we can expand that to 160 different individual nuclear species now and get the same runtime. And so we did that, and we're actually able to show that some things happened as the shock wave passes through the star. And you can note the change of scale here. 17 hours later, things look a little bit the same, but they're 10,000 times bigger now. If you look at a cut through of the star. We can also look at things like the 3D distribution of heavy elements that get spit out from this explosion. And you'll notice that the nickel and the especially nickel 60 sort of forms into these little bullets that are sort of moving faster than everything else. They've sort of outpaced everything else coming out of the star. These so-called nickel bullets are observationally seen and have been a bit of a mystery exactly how they form. And this recent work by Michael Sandoval, who's a recently graduated PhD student in our group, he was able to show that they just sort of fall out as a natural consequence if you do a simulation that has high enough physical fidelity and is run long enough. So that's that'll be I think that'll be the end of my astrophysics shilling here as perhaps the most exciting sort of thing that we do on Summit, because again, I want to reiterate, the machine's good for basically everything. We have lots of material science projects that go on the machine. I think an especially interesting one from the past few months has been this one on computer simulations of nanomaterial structure, and especially germanium selenide. So germanium selenide has been known to be an interesting material because it can absorb and emit light in very precise ways. And it has unique electrical and optical properties for use in things like optical sensors. If you take a material like germanium selenide and basically make a 2D sheet out of it, it reacts in a much, much different way. And the way that those materials have been studied in the past, a particular set of algorithms was able to predict the bulk sort of response of these materials and sort of get in the right ballpark as far as the minimum energy for these materials are concerned. But with new, better techniques, much more computationally intensive techniques, what was seen in this study is that when you have a 2D sheet of germanium selenide, the potential energy surface is very, very shallow, right? The difference between the first excited state and the true ground state of the material, which is what you're going to take advantage of, for example, to get light emitted or absorbed, is a pretty shallow little dip. And moreover, if you strain the material, if you torque it macroscopically, you can actually change the structure of that potential energy surface. And so you can actually change the response of the material by inducing a mechanical stress on it. That kind of work would have been impossible without having enough computational power to do a much higher precision study of the material in this case. Another recent success on the machine, I think, was this team led from the University of South Florida, who looked at simulating carbon at really extreme pressures and temperatures. This has, of course, been a topic of investigation for a long time, but the ability of this team to basically use all of Summit at once to do these simulations was a real tour de force. And what they found is that under extreme conditions, basically a shock wave forms once the crystal lattice is broken in diamond. And then the way that the crystal sort of heals itself is it turns into amorphous carbon, something like coal, for a while, and then finally is converted back into the hexagonal structure of diamond. That sort of passing through that time when you have only bulk carbon was a unique finding, one that hadn't been explored before. This is especially important to things like fusion energy, where the hydrogen fuel in a fusion reactor is actually kept inside a diamond capsule. And in inertial confinement fusion anyway, and then you basically compress that diamond. It's also important for the internal structure of carbon-rich planets like Uranus and other exoplanets that we know have diamond interiors at very high pressures and temperatures. In both of those cases, those are either places you can't do experiment at all. You can't realize those conditions in a terrestrial laboratory, or there are things like inertial confinement fusion where you can realize those conditions in a laboratory, but you only get to basically do it once. And because it's a very high energy happening, you don't get to do many of those trials in a given year. So those are a couple of the really recent things that we've done. One of the things that people do ask me is, you know, when I tell them that supercomputers are good for everything, but you know, what is it that supercomputers, especially modern supercomputers, are maybe uniquely qualified to do? And one of the things that I always return to is the idea, as I mentioned earlier, of turbulence. So, you know, turbulence is the last great classical physics problem. If anybody tells you they understand turbulence, you should probably put one hand on your wallet and back out of the room slowly, because they're probably trying to sell you something. And I think that a lot of the projects that are obtaining some of the most exciting results on our current machines, and will continue to do so on Frontier, all sort of revolve around this idea of turbulence. And I have some examples to show you of that. One is in large scale weather modeling. So not climate modeling necessarily, but actually weather modeling. So on, you know, seasonal timescales and lower. So this team from ECMWF, which is the European Weather Commission, used Summit to be able to do a global simulation of the atmosphere at 1 square kilometer average grid spacings. So they were able to reduce the size of the cells that they laid down on the Earth's surface from their usual canonical value of about 9 kilometers down to 1 kilometer. Okay, so that's kind of cool. You know, maybe is it just gratuitous throwing more resolution at it, and then because you have a big hammer, everything's a nail? Well, it turns out no. It turns out that there's actual physics going on at 1 kilometer scales that you cannot resolve with 9 kilometer sized grid spacing. Especially important is what's called wet convection. So how does water start to evaporate, rise, form into clouds, condense when it gets to the clouds, and then ultimately fall down as precipitation? That whole cycle sort of happens at 1 kilometer scales. And if you try to resolve that process using 9 kilometer grid spacing, you'll get it wrong. Or more to the point, you just won't see it happening. And you'll have to add that physics back in some sort of ad hoc way. Being able to perform simulations at this grid spacing, and to do so in sort of week-long timescales. Again, we're talking about weather, so it really matters how fast you can turn around a forecast. I could have a really, really detailed forecast, but it may take me 6 months to do it, which won't be much use to me next weekend when I want to figure out if it's going to rain or not, right? And so to be able to do this fast enough with the requisite physical fidelity is one of the real examples. And that resolution of that moist convection is all about resolving turbulence that forms when you turn the atmosphere over like that. We sort of understand how it works at large scale, but exactly how turbulence sort of rips up convective cells and renders them complicated surfaces and really controls the physics, that's really part of the problem. Another example of where turbulence really becomes the central question is in things like high pressure turbines. So that you, for example, use in jet engines, or they're also used on the ground to produce energy, for example. Of course, companies like GE want to be able to build very, very efficient jet engines. So they and also the more efficient we can make jet engines, the less fuel they'll use. If you can realize a 1% reduction in fuel consumption across a fleet of jet engines for an airline, for a typical American airline, for example, you'll save about $1 billion a year in fuel costs. That also will translate directly into emitting much less carbon into the atmosphere. But it turns out, of course, that fuel efficiency for a jet turbine is all about what turbulence looks like at the edge of the blades of the turbine itself. And tests can be done. You can have a test stand, for example, where you're going to look at exactly how efficient a particular blade design is. But what you can't do easily is basically take a picture of that at a high enough speed to be able to see exactly what the turbulent cascade is doing. But you can simulate it. And to simulate it effectively, you have to be able to get fine enough resolution so that you can resolve the turbulence actually forming in the first place because there's instabilities in the fluid flow, and then watch its cascade from larger scales down to smaller scales and see how fast it dissipates into heat. That's what this team from GE and the University of Melbourne, again, an international collaboration, was able to do with Summit recently. Got an unprecedented look at what turbulence actually looks like at the edge of some of these turbine blades. Fusion energy, of course, is something that the promise of fusion energy has been around for a long time. We are getting closer. It seems to, I think it seems to some observers, me included, that fusion energy is always 5 years in the future and independent of time. But I think there is real progress being made. And you can see that because there are now several startup companies that are all about doing either inertial confinement fusion or magnetically confined fusion, or other mechanical ways to confine a fusion reactor. But one of the most important questions for a fusion reactor is turbulence. Turbulence is what makes the fusion process sort of break down. The most famous, the fusion reactor that we're all familiar with, that big orange thing that's glowing in the sky when it's a nice pretty day like today, the sun uses gravity to confine its fusion products. We can't do that, so we use something like a magnetic bottle or the ilk. But it's been known for a long time that really the mix of stuff that you want is a mix of hydrogen and deuterium will provide you the best bang for the buck in a fusion reactor. But what people haven't been able to do is simulate both those two separate species, deuterium and tritium, for example, in a single simulation and be able to look at what the density fluctuations, what the turbulence does to the flow. This team from General Atomics and Oak Ridge were able to do just that, and they found that if you start with 50-50 deuterium and tritium, the flow separation between the two, they actually get separated in the bulk flow. They separate from one another, and the deuterium and the tritium fluxes are such that the tritium is better confined than the deuterium. The tritium sort of goes to the middle of the tokamak donut a little bit better, and it's held there, even though there are turbulent fluctuations around both of the flows. There's actually an experiment that's going to test this at the JET facility at the Cullum Center for Fusion Energy in Oxfordshire in the UK. So this is an example of, in some sense, simulation preceding experiment and sort of leading it along rather than waiting to try to explain experimental results after the fact. So, that's a taste of what we're doing now. And again, what I think is going to be a major push for Frontier, this generalized study of turbulence in a lot of different fields, ranging from engineering to climate to a lot of to almost everything else. And again, because you have large memories, you can have really, really high resolution, and because you're able to also do this in a reasonable amount of time, makes it incredibly valuable as well, especially the engineers. Engineers want to, for example, for this project that we saw earlier on turbine design, engineers basically want to be able to, for this to fit in their design cycle. They want to be able to do a run overnight, but they have to have enough physical fidelity so that it means something when they wake up the next morning to look at it. So that's all interesting, but of course, I think we'd be remiss not to realize that a lot of what we have been doing on Summit over the past couple of years has been all about COVID-19. Been trying to contribute somehow to the science behind understanding the virus, its spread, how it attacks the human body, and sort of what can we do about it. And as part of that, OLCF has been part of this thing called the COVID-19 HPC Consortium. Basically, it was stood up to provide rapid response to the pandemic all the way back in March of 2020. I had the first email in my inbox about it, I think, on March 19th, so less than a week after we all kind of got set home here in the US anyway, from the start of the pandemic. It's a consortium of lots of different places. All of the Department of Energy national laboratories that have big computers, several members of academia that also have big computers. Industry, a lot of cloud providers. So for example, Google, Amazon, IBM, other companies that have big computers, for example, BP. Some affiliates that provided some software and help, big computers at NASA and the National Science Foundation as well, and even some international partners sort of later in the game. And as a, what did we look at for the consortium? Well, a lot of the projects had to either do with basic science. So what did the virus look like? How was it built? How did it infiltrate the human cell? How did it evolve? There was a lot of, especially early on, concentration on therapeutics. What could we do to identify the targets on the virus that drug could attach to and thwart it, using small molecule design, for example, protein design, drug repurposing, what drugs were available that we could repurpose to attacking the COVID-19 virus. And then, of course, we also wanted to understand how patients actually reacted to the virus, their trajectory and their outcomes, medical technology, epidemiology, the detection of the virus, all those were open questions. At OLCF, we had, and still have, a couple of these projects running, 13 total projects, almost 3 million Summit node hours. That's approaching 10% of the machine, just to give you a sense of scale. And that represented, that's just about a bit more than half of all the projects that were allocated time on Summit for this. We had some from outside the consortium as well. Several of these projects also made uses of resources offered by other consortium members, for example, Google or the Texas Advanced Computing Center or IBM themselves, various other pieces that they would bring together to get the same job done. But Summit was really, really good at doing a handful of very important, very particular things. And I wanted to give you a taste of sort of what those kind of things were. So one of the things that Summit's particularly good at, because to zeroth order, it's just a big pile of GPUs, is this particular computational technique called molecular dynamics. So molecular dynamics basically treats the interactions, the electrostatic interactions of atoms and molecules like a Newtonian physics problem, and takes a look at how they interact with one another. So there was this one project, here's an example of a project like this that made extensive use of molecular dynamics on Summit to be able to come up with some fairly interesting findings. And it was looking at the conformational dynamics of the spike protein. So I think we all intuitively know what the spike protein on the COVID virus is, right? If you close your eyes and think about the bumper for every newscast you've seen over the last 2 years, with that one image of the coronavirus looking like an orb with things sticking out of it, right? I think everybody in the world, it's almost a universal language, sort of an icon for the human race at this point. Those things sticking out of that orb in the middle of the coronavirus are the spike proteins, and the spike proteins are what what the virus uses to gain egress into the human cell. So that spike protein binds to a certain receptor on the surface of the human cell called the ACE2 receptor, basically unlocks that receptor, and then is able to inject its RNA payload into the human cell and use the machinery of the human cell to replicate itself. So from the earliest days of the pandemic, from a therapeutic point of view, it's been really important to try to figure out, is there any way I can thwart that sort of key and lock dynamic? Can I put something in the way of that key trying to get into that lock and unlocking it so that it can't happen? So the spike protein can't dock effectively with the ACE2 receptor, and therefore can't let the virus, doesn't have a way to get inside the human cell and be able to have access to machinery that will enable it to replicate itself. It turns out that even though that picture of the spike is a nice artist impression, the spike is constantly sort of moving. proteins in their own sort of electrostatic field do a lot of moving. They change shape. There's details on that spike protein that you don't see. It's not just a spike. It just sort of sticks out and has a, as you see here, sort of has a flat head. Another thing that happens is those amino groups, those proteins that are part of that spike protein, pull glycol groups onto them, pull alcohol, fats, and other things, but mostly glycol groups. And the glycol groups sort of adhering to those proteins do a really good job of shielding the spike protein from antibodies in the body, because the antibodies can't identify that protein anymore as something it wants to attack. The virus is sort of using the same sort of strategy I was just talking about that we were trying to figure out with drug repurposing or small molecule design, to basically cloak itself from antibodies in the body. The other thing that the spike protein does is it basically has a flip top. There's a part of it, there's a part of the protein that on the top of it that basically either flops open to allow docking with the ACE2 receptor or stays closed most of the time. And how much glycol is actually adhered to the spike protein actually impacts that opening and closing. That's what this project was all about. Sort of figured out exactly what the glycosylation of the spike protein looked like. They also found something particularly interesting that was just sort of a gravy in the study. There was this one particular antibody, BD368-2. Its epitope, that is the part of the protein that it wants to attach to, is exposed to it where it doesn't matter if the S protein is in that up or down state. So this particular antibody can always find the spike protein, no matter what state it's in, and can attack it. It needs to be able to marshal its buddies in the immune system to be able to effectively attack the virus as a whole, but it can always find it. And some therapeutics have in fact tried to target this particular antibody and help it along, if you will, because of this finding. So that was a lot of molecular dynamics to study the spike protein per se. But again, because proteins interact with themselves and with the water that's around them and with sort of everything else in the environment, it became pretty obvious pretty fast that really you needed to model the whole virus all at once with all the proteins. But this is a pretty monumental computational feat to think about trying to do, because the entire virion envelope of the virus, even though it's the SARS-CoV-2 virus is not a very big virus physically, but it does have there's at least 300 million atoms. This is a really big computational problem. Again, because Summit's so big and can do molecular dynamics so efficiently and effectively. This one team from UCSD actually won a Gordon Bell Award, which is a famous supercomputing award last year, by doing just that. They modeled the entire virion coat of a single SARS-CoV-2 virus, including the spike proteins and sort of the stuff that makes up the orb, if you will. They've now started to push beyond that, and they're modeling this, and they're putting the whole virus in basically a drop of water to see how effectively the virus is transported, basically in aerosol form. How, in spit, for lack of a better term, how effectively it can be still active in the environment, and how long before it gets damaged because the water starts to go away. This was a real tour de force calculation, and again won this award. And I think it's actually gone to help understand, has helped us understand exactly how the virus is actually passed from person to person. As I'm getting to the end here, we've also got a couple of projects that have to do with COVID that really used artificial intelligence and machine learning techniques to figure out things. So this one from Jennifer Diaz from Icahn School of Medicine basically used a particular kind of machine learning algorithm called a random forest to be able to try to figure out how combinations of drugs, how they interacted with one another, and in turn how they would interact when they tried to attack the virus. in a way that was much better than just brute force trying to take all possible combinations of these 22,000 drugs at a time. And now it's up to 1 million individual drugs in this drug screen. There's a handful. They figured out about a hand. Literally, I think the number was 17 out of that first 22,000 that were worthy of following up in the lab. There are other AI and machine learning techniques that have been brought to bear, including the use of this, what's called a deep learning language model using encoders. So it's this BERT model, actually from Google. So if you do a Google search nowadays, the odds are this particular machine learning model, BERT, is going to be used to try to figure out what you're actually looking for. It's basically a machine learning model that was trained on a corpus of texts and can figure out meanings of words through the context around those words. Turns out you can repurpose that technology to figure out molecular sequences, molecular chemical sequences. Again, that's a sort of a language. So you can repurpose the BERT model, train it on a set of chemical sequences, and let it do the work to figure out if you're going to have, for example, an effective drug. They were able to retrain the BERT model by running 2 hours on all of Summit's processors and actually be able to get there. And this work was a finalist for that famous Gordon Bell Prize. And just as an aside, we just finished a paper that sort of is telling us about how people are actually using artificial intelligence and machine learning in simulations and in the work that's already being done on Summit. And it turns out across all of our allocation programs, about 40% of the projects have some use of artificial intelligence actually happening in the project right now. I think the age of artificial intelligence has arrived. They use it in various ways. Some of them only use it to try to figure out the results of the simulation and be able to gain scientific insight from those results after the fact. Some of them use what are called surrogate models. They use subgrid models. They use AI to replace pieces of physics that they can't resolve in situ in the simulations themselves. Some of them use it to design the set of experiments that they're going to do. Which runs with which parameters am I going to do that will most effectively allow me to understand exactly what's going on in this case. We found it across fields of science that sort of everybody is using some amount of AI in a lot of things. So with that, I'll end my core dump and we can explore the questions. And I'm of course happy to answer any new ones. I haven't been able to peruse the list of questions yet, but I guess Herb was going to help me curate those. Is that what I understood?
Yes, well, I've been looking over the questions here, and there's been side chats going on, as you'd expect. I
love this question.
And many of the questions.
There's one question by John.
Many of the questions have been answered, and William Fan and others have been chatting quite a bit. So I'm looking for some questions specifically that may not have been answered.
Right.
Well, just
let me
comment that many of the people are paying attention to the talk and weren't necessarily paying to the chat box.
I understand.
So I encourage you to at least the significant ones, perhaps have Bronson summarize, but that's up to you all.
No. So let me comment on it. I'm looking at this comment stream about where do you learn to program a machine like Frontier or Summit? I think it's a really good question, and I see that there's been some pretty sophisticated answers to that question, sort of pointing everybody. I can't imagine there's another field of science that's still as caught up in lore as we are in HPC. It's still very much a sort of medieval master and apprentice relationship when it comes to training people, high-end HPC practitioners. I think something that people don't appreciate, and maybe members of this audience would appreciate, is exactly what language do you write high-end HPC codes in? And I can tell you, 60% of all the cycles on Summit in a given year are consumed by Fortran codes. Still. And there's a reason for that. And it's not just because we're old and crusty. It's that the syntax of Fortran allows the compiler to help you. You have to be explicit about what you're doing memory-wise. You have to be explicit about what you actually want the computer to do. Because of that, Fortran still rules the roost when it comes to performance. And has been said about supercomputing in the past, there are three important things for supercomputing: speed, speed, and speed. Because I'm consuming a resource that costs a lot. I can tell you, for example, the cost recovery on Summit, the recovery rate we would charge a company to come in and use Summit is about $8 a node hour. 4,000 nodes, that's $32,000 an hour. And let's say you need 100 of those hours, you're at $3 million to be able to do a simulation. And that's just one. So it's a precious resource. Speed is of the utmost importance, and because of that, a lot of people still use Fortran. There's still stuff. There's stuff that's catching up, but I like to say that people have made a lot of inroads in using what are called domain-specific languages. So writing a language that's for a particular scientific field. I like to say science has a domain-specific language. It's called Fortran, because Fortran has multidimensional arrays, which are like matrices and vectors. And best I can tell, that's what Mother Nature does. So at least my understanding of what she does is predicated upon that. So
Bronson, I've got a question. The program is so broad, and there are so many worthy projects. How do you allocate time? Is there a user group that carefully goes through? Is it internal to Oak Ridge, or is it include the whole country?
It's a wonderful question. We have two primary allocation programs. One's called Insight, one's called ALCC. ALCC is maybe what a lot of this audience would be used to, right? It's the Oscar Leadership Computing Challenge. So the proposals go to DOE and individual program offices, fusion energy sciences, basic energy sciences, biological and environmental research, nuclear physics, high energy physics, for example. They sort of, in collaboration with Oscar, figure out what are the most important scientific problems. Let's get them some time on the machine. They do a scientific review like they do with any other grant, that kind of thing. That's very much in keeping with what people might be used to, for example. That's only 20% of how much time we give out. 60%, the bulk of what we give out, is under the Insight program. Insight is open to anybody on the planet, like I said before: industry, academia, DOE, foreign or domestic. It has a two-stage review process. The first stage is computational readiness, which is performed by those liaison and catalysts that I talked about earlier. They basically look at the proposals and say, yes or no, can you make use of Summit? Can you really make use of something this big? And do you really need to make use of something this big? After that set of reviews, we, as the LCF, we seat a bunch of scientific review panels and have them rank the science for each one of these fields. And we basically have to field about 18 of those panels to cover all the fields of science. It's actually really hard to seat those panels, because basically everybody in the US who can make use of the machine writes a proposal every year to Insight to make use of the machine. Actually, in that regard, the pandemic's been a bit of a boon for us to make those all virtual, so we can get our reviewers from Australia and Japan to join the conversation without having to fly to DC, for example, to set it a review. But it's incredibly competitive. We're typically 5 times oversubscribed. We get 5 times more ask than we are able to provide in a given year, which is a remarkable rate of oversubscription. Frontier will help with that, but I actually think that there are folks out there who could make effective use of the machine, who've now sort of not gotten an insight 1 or 2 years and they give up. So I'm hoping I see part of my job is trying to re-encourage them to apply. I think there's even more demand out there than what we see, even at the very highest end of high performance computing.
Is there a limitation on how much time can be given to somebody who wants to pay, like a corporation, versus basic science?
Yes, there's no a priori, partitioning of that, but once we've taken 60% of the cycles for Insight and 20% of the cycles for LCC, there's only this much of a year left. And so no matter if they can pay or not, we've already committed the hours and told our sponsors that's what we're going to do with them. So their request has to fit in here. I should also tell you that even though we do have a cost recovery rate, frankly, it's so expensive that nobody's ever taken us up on it. We have a waiver for industry to be able to use the machine that says basically you're going to publish everything that you find, right? So there's some companies who come that said we want to do a proprietary piece of work on here, and we've said here's the cost recovery rate. You're sure you don't want to do something that could be published in the open literature? And they've sort of changed their mind. Yeah. But it's good for them because ultimately they use it as an argument to their management. Hey, buy me a supercomputer. Maybe not one the size of Summit, but buy me something that will have significantly more capability than I have now. And I'll be able to do this much more work.
Who else has a question?
Herb, I have a question, if I may bring it up. One of the most, by the way, this was an excellent presentation. I really appreciated it. How well are you able to calculate the amount of gold is being produced in neutron star mergers? And the observation of Lagos told us where to look, and then we saw this spectroscopy. Were you able to determine how much gold and then how much uranium is being produced in these mergers?
Thanks, Bob. That's a really good question. So what we relied on up to this point is doing those simulations, basically pulling out the temperature and density and timescales for the explosion and the expansion, and then post-processing those data to try to figure out how much gold, how much uranium, how much plutonium, how much nickel-60 is formed. Right. So that's fairly effective, but I think you can already see the problem, right? For some of those processes, you eat energy. For some of those processes produce energy, and they change the density and temperature in situ while you're actually doing it dynamically. And that was part of our motivation to try to get these big nuclear networks actually in the simulation, running alongside all the rest of the physics at the same time. We're pretty confident that with 160 species, we can get most of the burning that happens during the supernova explosion. But to really do gold and uranium and plutonium, we have to model what's called the R process, the rapid neutron capture process.
Right.
That requires thousands of isotopes, but we plan to do it on Frontier. We think we can do thousands. Turns out with GPUs, you have enough memory, flops are almost free. If you give them a simple enough task, they can do almost anything fast enough for you to get there. So we plan to do our process nucleosynthesis in situ on Frontier.
May I ask one real quick question too? You mentioned that carbon was an important part of what you're doing, and most of what we see in the interstellar space is carbon and water. Mm-hmm. And we know that there's a lot of C60 out there and probably a lot of C70. And the question, is anybody working on the production of C60 and C70 and other carbon clusters to explain the diffuse interstellar bands?
That's a really, really good question. And I think it goes back to what Herb and I were saying earlier, there's not enough atomic and or molecular physics going on right now to be able to help us explain astrophysical observations we know are going to be coming online, right? Okay. There are large synoptic surveys that are going to be absolutely critical for us, for example, to know exactly how much water there is in interstellar molecular clouds. And we're really going to be in a bad way unless we can somehow find a way to fund some more experiment to be able to figure out what those things actually look like, because we don't have a great handle on either one of those questions right now.
Thank you.
Bronson, I did isolate some questions that haven't been answered. There's a comment that says, "This fantastic presentation, Dr. Messer. When will Frontier be running at exascale?"
It's a really good question. So the machine's up and running right now. It's a complicated beast. It typically takes us not quite a year from the time we first get cabinets on the dock to where we have a machine in production. I think we will beat that with Frontier. We had the first cabinets arriving on the dock late last October. We now have all the cabinets here. I expect that we'll be in production before the end of this year. But beyond that, it's really hard for me to tell you. There's lots of things that go on, things you wouldn't expect, things we do expect. You know, there's, I think it's the Donald Rumsfeld quote, there's the known unknowns and the unknown unknowns, right? We've already run into some unknown unknowns and known unknowns. One of the things people don't think about is electronics like this typically suffer from high infant mortality, right? If something's going to go wrong, it goes wrong quick. Turns out when you buy thousands of components at once, lots of them fall out. So we're very used to being able to roll those back in. So my hope and my guess is that by the end of the year, we'll have Frontier in full production. We've certainly told our sponsors that we're going to allocate the machine for next year.
A question about logistics.
Mhm.
How long does it take to start and stop a program?
That's a really good
Does
question.
the principal investigator do it himself?
All the processing currently on Summit and its predecessors has been done with batch processing. So you submit a script that basically goes into a queuing system. The program starts at some point and ends at some point. Hopefully it exits gracefully, right? Hopefully you get what you need and it just and the program stops and the batch script exits gracefully. Kind of simulations I do with Core Collapse Supernova, because we have to get in line over and over again. We just let it run through the end time and we get shut off, and we rely on having dumped the state to disk at various times so that the next time we pick up, we just read that state off the disk and we continue with the simulation after that. So you have to teach, the extra thing you have to learn is this queuing language. It's pretty simple. Typically these batch scripts are sort of a dozen lines, sort of to kick off the program, start it running, and tell it where to dump its output.
Bronson, there was another question that wasn't answered. What happens to Summit when Frontier is fully operational?
Yeah, so we're going to run them side by side for about a year. And then Summit will be out of maintenance. So our maintenance agreement with IBM will come to an end. And we will probably evaluate whether or not we'd like to pay for another year of maintenance, depending on the return that we're getting from that investment. If I had to guess, we'll probably run Summit for a little longer than 1 year after Frontier is fully operational. But that's only a guess on my part.
Well, if you have such a big backlog of users, doesn't it make sense to keep Summit going on as long as possible?
This is, you know, in my role as the user advocate to our director of operations and our center director, that's exactly the argument that I'll use.
We have another question from Carolyn Krauss. Stardust question. Did all the elements on early Earth come from supernova?
Everything in us, every atom of iron in your blood, every piece of gold in the chain around your neck came from a supernova explosion, pure and simple. More to the point though, what we think is most of the heavy elements, heavy meaning astrophysicists heavy, hydrogen, helium, and metals, the whole rest of the periodic table is metals. All the metals in the universe, except maybe for a little bit of lithium, came from a supernova explosion and or a neutron star merger. But we think more to the point is almost all of the heavier element enrichment in the Earth came from a single supernova, a single nearby star that exploded before the birth of the solar system. probably enriched the entire solar nebula. So it's not a combination of 2 or 3 going off. We think a single supernova did it. So we owe our entire existence to the death of a single massive star.
We have a number of comments on what an accomplished person you are, and what a good explainer you are. So cutting through the complexity so that everybody can understand it and get excited about science. So Eddie Mansfield said we need more people like him.
We have a couple hands up still.
Yes,
Bob
John.
Sadlow,
There is
John Gunning.
a question that you might have missed from Jim Rome. If your job runs for a week,
What was that?
I have a question.
Okay, thought I heard my name. Yeah, when I left ONL at the end of 13, one of the challenges was they were like building more and more AC units and pipes for cooling. So, I mean, you gave me a number, but that doesn't really mean something. Have there been significant advances in decreasing the heat generation?
Yeah,
By
that's,
the
yeah,
units,
that's
and
what-
like sort of what fraction or something like that?
Yeah, so basically, when we started to kick off 10 years ago, when we started to build Frontier, people wanted us to be able to fit it into 40 megawatts, and people thought it was impossible. And it's going to fit into 30 megawatts, but still, that's a lot of heat to dissipate. And so we will be. It has significant. We've had to significantly increase the infrastructure for cooling, especially, but we are using some tricks. So for example, instead of using water that sort of comes in at 50 degrees and then gets heated up to 100 degrees, we're coming in with water that's almost 80 degrees and letting it heat up to about 120 degrees. That way we don't have to run chillers on the water except for the height of summer, perhaps. That's a huge cost savings and a huge decrease in our thermal load. Without GPUs, and actually the big computer in Japan that is currently being us does this, uses all CPUs. They have to use 80 megawatts of power to power that machine, right? We could do it, but it's not a cost-effective notion to do. And without GPUs, we'd probably be much worse off when it comes to Frontier. We wouldn't be able to realistically power the machine and dissipate the heat.
So per unit of computing, there's been a significant reduction in the heat generation. Is that true?
Yes, absolutely. But the GPUs are probably the single biggest factor when it comes to energy efficiency for big computers, period.
But the higher temperature of the cooling water, does that affect the lifetime of the electronics?
No, because the GPUs get hot enough that the delta T is big enough.
Okay. Okay, a question from Bob Sadlow.
Okay, thank you, Bronson, for your excellent presentation. I want to go back to, you said that you have like 5 times more business than you can accommodate. Does Argonne have that similar thing in other high performance computing centers throughout the nation?
I think 2 separate questions. So that Insight program, we run together with Argonne. So
Okay.
that 5X is for both of us. And we sort of treat the program as one. We've actually moved some people around. People have asked for time here. We've moved them to Argonne. They've asked for Argonne, then we moved them here. But that 5X is for both of us. For other computing centers, frankly, no. The answer is no. Our sister facility called NERSC at Berkeley Lab, they do not have that degree of oversubscription. The NSF centers do not have that degree of oversubscription. The NSF centers are more like maybe 2X, maybe not even quite 2X. And it's because there are problems that you just need a really, really, really big computer to do. And if you have one of those problems, you have nowhere else to turn, right? And that's why I always say that Summit and now Frontier have a lot more in common with the Hubble Space Telescope and with the Large Hadron Collider than they have with a pile of laptops. Right, it's a unique scientific instrument and one that's not replicated in very many places on the planet.
Thank you.
Well, we've reached 1:17. Are there any other questions that are really burning?
if somebody wants to, if somebody can collect those, I'm happy to answer them via email. I'm sorry, I probably have to get to my next meeting. I think I'm late already, but
Okay, well, we won't hold you up. So thank you, Bronson. The audience can now unmute and show your appreciation.
thanks very much, everybody. Really appreciate it. It's great.
Clapping
Go
now.
And thank you for coming, everyone. We hope to see you next month to listen to Colleen Iverson speak about the environmental field studies related to climate change.
Herb, could you and Ellen and your wife stick around a second? I want to ask a question to you
Sure.
three.
Sure.
We are still recording, by the way.